The input-output operations can be organized in two different fashions. In the first approach, after the I/O operation starts, the controller returns to user program only when the I/O is completed. In this case, you should stop the CPU from going any further until I/O operations complete. So, for example, you have a wait instruction which keeps the CPU idle until the interrupt arrives from the I/O controller. But then you would have a wait loop, always checking if there's an interrupt or not and keeping the CPU idle. But in this case, the CPU can execute either a user program or wait for the I/O of that program to complete. The CPU is not able to proceed with other processes because it's executing in a loop that wait instruction until I/O is completed. Of course, this is not a very efficient manner, especially if you consider that the I/O device is typically thousands of times slower than the CPU itself. So we need a better approach, which is the second one. In the second case, after the I/O is triggered, the control returns to the user program without waiting for the I/O operation to complete. Now, there is a slight problem here because you have made, for example, a read request. You're trying to read something from the disk into a variable. Now you initialize the read operation, and if you just continue with the next instruction, which would be making use of that variable, you would have a real trouble because that variable is not initialized yet because read operation is not completed. There are cases in programming where we want this to happen because the next instruction after read actually does not depend on the result of that read operation. In most cases, it depends. So there are ways of dealing with this. We'll come to that. But the more important thing is we let the CPU continue. Maybe not with this process, but we will see in the following chapters that if we allow the CPU to continue rather than waiting as we did in the first approach, if we allow it to continue, maybe it will not continue with this process, but with another process. So it will use the time when that slow I/O device is doing I/O. It will use its time for another process to make someone else happy. And when this I/O is complete, it will return to this one. Okay? So here we make use of some system calls, which is actually a call and information to the operating system about what you want to do, actually what you want the operating system to do on your behalf. So it's a request to the operating system to allow the user to wait, for example, for I/O completion. That process which made the I/O request might tell the operating system to wake that process when the I/O is complete. This is just like I make a request and I tell my wife to wake me up when that happens. Okay? And I start sleeping. Meanwhile, another process could be using the CPU. When that I/O operation is completed, that process that was sleeping will be awakened and it will continue. Okay? So this way we could have multiple devices doing I/O. Like process P1 might want to read something from the disk. Okay? So it says, wake me up when the disk has provided me this information. The CPU switches to another process, P2, which executes some instructions, and at that point it says, display this thing on the screen and wake me up when that is done. The CPU switches to yet another process, say P3, which executes some instructions and at some point says, wake me up when you send this bit of information over the internet to this address. the CPU will switch to another process P4. Meanwhile, process P1, the request of P1 will be satisfied. That information has been read from the disk. So the CPU, while executing P4, it gets interrupted, saying the data is now ready. So the CPU will first handle that interrupt service routine, and after that it will continue with P4. And when it is ready, when P4 is completed, or maybe the CPU, the operating system decides that it has given P4 the CPU for a very long time, so it may say, okay, let me switch to P1 for a while because its data is now ready. And it will go to P1 and execute the next instruction of P1, which dependent on that read operation. Then maybe to P2 or P3 or back to P4, I don't know which one. It's up to the operating system to decide on that. But the important thing is, as we have seen here, P1 was doing some disk I/O, while P2 was doing some graphics I/O, while P3 was doing some network I/O. It is possible with this second approach to have multiple I/O operations simultaneously. Remembering that these I/O operations are typically very slow, overlapping these slow operations in time is it exhibits much better performance composed to putting these slow I/O operations in a sequential manner, one after another. If you let these slow things run in parallel, the overall time from beginning to the end of these three operations would be much shorter than having them in a sequential manner, because in this case you cannot benefit from parallelism, and the total time it needs would be the sum of them, whereas in the other one you benefited from the overlaps in time. So the operating system needs to know which of the devices it has is in which state. Like, my disk is currently busy, my graphics card is currently busy, my network card is currently available. So when process P3 wants to send something over the network, it will look at the network card, see it's available, and do it. If P3, rather than using the network card, if it tried to read, say, again from the same disk as P1, it would have to wait, because in that case, in the device table for the disk controller, it would say it's busy. Okay, so therefore the operating system needs a device status table which tells the status of each device. So typically there is the type of the device, the address, the ID of the device, and the state, whether it's busy or reading, writing, available, not available, whatever. And the operating system will index into this I/O table. Each I/O device would have a different number, and that number would be the index in that table. So we say the operating system indexes into the I/O device table to determine the status of that specific device. And if it's going to do some operation, then it would be modifying that status in that table, and also modify the table entry to include the interrupt. Also, as I said, it's possible to write your own interrupt service routines and change the interrupt table. Don't forget that. So, about the storage structure. When we say storage, we mean the main memory, which is your RAM, your secondary storage, which is typically your disks or other types of storage devices, your hard disks, and your solid state disks. Typically, hard disk, solid state disks are type of secondary storage devices. There are also secondary storage devices like tapes, but you don't see them very often. Typically, they're used in systems like mainframes, or used for taking huge backups. For example, if you want to transfer a huge amount of data, uh, what you would expect is not correct. Internet sometimes is not the best solution. This, for example, once happened to us when we were trying to transfer a huge genome database from Germany. We looked at how much time it would take to transfer that huge database, and we realized that it would consume most of our bandwidth for a very long time. And also, if troubles happened during the transfer, resuming from where it was left would be troublesome. So instead of that, it was easier to transfer the information with a tape, which is much faster than doing it over the internet and more robust. Anyways, for the case of main memory, only large storage media that the CPU can access directly are stored in main memory. It provides, what's nice about main memory is it provides random access. What does that mean? You can access any address in the memory at the same time. What I mean by the same time is the time it takes to access a specific address doesn't matter, doesn't depend on the address. You can access any part of the memory. It's always consuming the same amount of time. Typically, the main memory is volatile. That means no power, data is lost. So you have to keep these types of storage devices, the main memory, typically you have to provide the power all the time. That's why you shut down your computer, memory is gone. Or if, for example, you're not using a laptop but a desktop computer and you have a power shortage, or if you were using a laptop and suddenly your battery dies, you will be losing everything in memory. So it's volatile. Secondary storage, on the contrary, is typically non-volatile. That means no power, still it remains. Because the problem here is typically the main memory is electronic circuitry that needs power to keep the information 0 or 1 in the flip-flops. Whereas in the case of secondary storage devices, especially in the case of hard disks, of course not in the case of solid disks, you make use of magnetic information, a magnetic medium where you can change the direction of magnetism to represent 0 or 1. So when the power is off, still it will keep its direction. So that's why it's non-volatile. Typically, the hard disk is made of some rigid metal or glass, which is covered with some magnetic material over which you can store the information. The disk is the disk surface is actually composed of concentric circles. That means circles with the same center. So it's at the this is just like, now consider this is a CD, by the way, not a disk, but just take it like you have one circle at the small circle at the very center, a larger one, larger one, larger one. So consider it just like several circles, all with the same center here. Okay, so that's what a disk is like. Now the disk would have two surfaces. Sorry, the disk actually would be like, now I have three disks here. This is, okay, Jedrotal. On top of it, I will have Deep Purple, and on top of that, I will have the Animal CDs. But it would be like, maybe I should be using my pinky. Sorry, I couldn't manage that. It's just like this, okay? Here I have the case of a three-platter system, okay? Each one has two surfaces, two different surfaces, and I have three such platters. Okay, and on each one I would have these circles which are called the tracks. So I would have, say, 80 circles on this surface. So I have 80 tracks here. Just on the other side, I would have similar 80 tracks, and on each one, on each side, I would have such 80 tracks. Now, if I have three platters, I have six surfaces. On each one, I have 80 tracks. So in total, I would have 480 tracks. Rather than that, what we do is the following. If I have 80 tracks, 80 concentric circles, in other words, on each surface, just consider the innermost track on this surface and on this side, inside, inside, on all sides. Now, these six innermost tracks would appear to be just like a cylinder. So that would be my innermost cylinder, say cylinder 0. If you look at track 1 on each surface, I would have 6, again, such track 1s. So that would be cylinder 1, cylinder 2, 3, 4, all the way to cylinder 79 for 80 cylinders. Okay? So the tracks, each track at the same index on each surface together would form me the cylinders. We also split the surface in an angular manner. Say I had 6 sectors for the sake of simplicity. Okay, if I had 6 sectors, these would be just like slices. Okay, I would have sectors of degrees, 60 degrees, and now I can talk about cylinder. But remember, the cylinder does not differentiate between the tracks. If I tell the cylinder number, at least I know which of those 80 cylinders it is. If I also have the surface number, I know specifically which track it is. Like, for example, if I say cylinder 20, that means cylinder composed of track 20 on each surface. If I also know the surface number, then I know specifically which track. If I also know the sector number, I don't need to read the whole circle, but it means a portion of that circle. So that would be my sector. Now, on this device, I have 6 surfaces. I might have bought a secondary disk on my computer and say connected over USBs, for example, for backup purposes. On that one, I would have 2 platters, so 4 surfaces, in other words. The first one with 3 platters would be of some brand with, say, 80 tracks. The other one could be one with 60 tracks and less surfaces, whatever. Of course, this would affect the size of the disk, but the important thing is each disk could be different. Okay, so it is a disk controller that deals with all this. How many cylinders we have, how many surfaces we have, how many sectors we have, and also you want to read something from this address. Okay, a huge hexadecimal address, and we have to convert that sequential address that's given by the CPU into the correct surface, cylinder, and sector numbers. Someone has to do this calculation and then send the read-write head onto the correct cylinder, because remember this, if you're talking about cylinder 20, and if my read write head is on, say, cylinder 79, I have to move it from 79 to 20 to go to the correct cylinder. Now I have read write heads, many of them at the same level, so they all move in and out together. So if I move one, all of them will move there. But now I have all read write heads going to the same cylinder but on all surfaces. Which one do I mean? Select the correct surface. So ignore the other heads, only look at this one. But still, the data I want to read is here. My head is here. So I have to wait until this disk rotates and the correct place, correct sector comes below this head so that I can start the read operation. It's a disk controller translating the sequential address to the correct sector, platter, surface, cylinder numbers, and moving the heads, waiting until the correct sector comes under the read head, and then transfer the information from here to the local buffer of the disk controller. All this is managed by the disk controller. No one else needs to deal with this. No one else has to deal with different types of disks, for example. That will all be handled by the disk controller. Now, this is true for all I discussed is for the hard disk. For the case of solid state disks, it's different. In that case, in the case of solid state disks, we don't have any platters, surfaces, read write heads, cylinders, or whatever. A solid state disk is a special type of hardware, electronic circuit, which stores the information in a non-volatile manner as opposed to the main memory. It's a different kind of electronic circuitry. We will not go into that detail. But the important thing is a solid state disk, SSD disk, is non-volatile, which means when there's no power, still it will keep the value. And it's becoming more and more popular because it is much, much faster compared to the hard disks. But it also has its downsides. It's more expensive per byte. That means if you try to store 1 megabyte of information on an SSD disk or a hard disk, SSD disk is typically much more expensive compared to a hard disk. And also the number of times you can read write from an SSD is typically less than a hard disk. So that's why we don't use only SSD disks on, especially on server systems. We use the SSD for some purposes and the hard disk for other purposes, and we use a combination. We even have now hard disks that are sold with an SSD on top, which is working as a cache. So the frequently used data is transferred into the SSD part, and the rest is stored on the hard disk, whatever. So the storage system itself is organized, in a hierarchy depending on the speed of retrieving information, the cost of storing that information, cost of that device, and whether it is volatile or non-volatile. So in this hierarchy, we have something we call the cache, which is actually yet another copy of the same data, but typically it is stored in a place which is much faster than the layers below. And for each different type of device, we have a device driver. You already heard about drivers when you're trying to install a new device on your computer system, which provides a uniform interface between the controller and the kernel. So all those specific details about the new device are handled by the device driver, so that for the kernel, it's not important what the specific requirements are. It's just a uniform interface for the kernel. So this is the hierarchy of devices. what you have at the top is the fastest one. So as you go up, it becomes faster. But typically the amount of data you can store gets smaller, and also the cost typically gets higher as you go up. When I say the cost, I mean the cost per byte. We have to normalize it. The cost of storing 1 byte or kilobyte, megabyte doesn't matter, but 1 unit of byte, it will cost more dollars at the top and fewer dollars at the bottom. However, retrieving data from a device at the bottom will be much more slower compared to a device at the top. So at the very bottom, let's start with the slower ones. At the very bottom, we have the magnetic tapes. These are sequential devices. So if you want to read, I'd say, a byte at address 1000, you have to start from 0 and skip 999 of them. Then you will be able to read the 1000th. Well, if you want to read the millionth, then you have to skip 999,999 bytes and then read the next one. So the performance depends on the index. That's the major drawback with the magnetic tapes. These tapes typically store a lot of data, and the cost is very low, but these are extremely slow, and it also depends on the index of the data you're trying to read. These are to be used typically only for backup purposes. You cannot use it in regular operations because they're very slow. The optical disc is things like the CD because it works with laser. There are also other types of optical discs, but they make use of typically a laser to read or write information. These are typically faster, much faster than magnetic tapes, but slower than the hard disk. Some of them are read-only, some are read-write. The cost is a little bit higher than magnetic tapes, but lately it has really become quite cheap. The hard disk is faster, but still the hard disk is too slow for the CPU to use in its regular operations. The CPU deals with the main memory. In other words, your program has to be in the main memory to be executed on the CPU. But remember, the main memory is volatile, which means when the power is off, everything is gone. So when I try to run a program, it wouldn't be in the main memory because when I powered on the computer, it was empty. The main memory was empty. So it is stored either on the hard disk or the faster solid state disk. But both of them, even the solid state disk, is much slower compared to the main memory. So we will bring the program from solid state disk or the hard disk into the main memory, and the CPU deals with the main memory. Even the main memory is slow for the CPU, so we will be caching the parts that are frequently used, at least for the last few tens of seconds, into the cache, because cache is faster, which is again volatile, and much smaller compared to the main memory. So we cannot bring everything in the main memory into the cache. Only the parts that are frequently used are brought into the cache, so that the CPU typically reads from the cache. And if something is not found in the cache, it will have to go to the main memory and read from the main memory. But the moment you read from the main memory, hardware in the background makes a copy in the cache so that the next time you need it, hopefully, we cannot guarantee that, but hopefully we will find it in the cache. In that case, it would be a faster retrieve operation. We will be discussing these in more detail. But when executing an individual instruction like add A and B and put the result in C, to do the addition of A and B, you have to get the value in A and you have to get the value in B. and send them to the ALU for the addition operation. So the CPU will transfer the variables A and B into registers, say AX and BX, doesn't matter how you call the register names, but it will bring them to two different registers and tell the ALU to do the operation. So the ALU reads from the registers, does the operation, and the result will be placed in another register, either CX or accumulator, a specific register, and then that will be copied to the main memory. Meanwhile, the next operation will be executed. These are all discussed in CMP240 and more in CMP344. Caching is an important concept that's used frequently in computer science at different levels. You can have caches that work at the hardware level. You can have caches in the operating system or even in your own software. You can use it under the name caching or buffers or different names, but it's basically the same idea. The basic idea is as follows. Whatever is being used frequently, keep it in a system that is much faster, because transferring it from a slow system to a faster system, well, that will be an overhead. It takes time. But if you're going to use it very often, then in the follow-up uses, you'll be retrieving it from the faster system, so it will compensate for that overhead we had in the beginning. But this works if that thing is to be used frequently in the future. Now, that's the problem with caching. You have to estimate what's going to happen in the future, and that's difficult to say. But there are ways of making such good estimates. Of course, your estimates might fail, so you should define your caching mechanism such that if you fail to properly estimate, well, you will have some decrease in performance, but nothing will go wrong. Still, the results should be as expected. In other words, the results might be delayed. I can tolerate for that, but the result should not be different depending on whether I find it in the cache or not. As long as you design it that way and your estimation for the future works fine in general, you have a very nice caching mechanism. That's the idea. So the information in use is copied from that slower device into the faster device temporarily. The faster storage, which we call the cache or the buffer, typically we call it the cache, is checked first to determine if the information is there. If it's there, then use it. That's a nice scenario. It's fast. If it's not there, then you will have to go to the slower device and read it from the slower device and use it. Meanwhile, make a copy in the faster device so that in the future, when you need it again, you can find it from there. So the basic idea here is the principle of locality. That's how we call it. That means if I have read some information, if I have used some information somewhere, the next information I'm going to need, the next piece of data I'm going to need is probably somewhere in the vicinity. Note that I said probably, I cannot guarantee that. But the basic idea is like, for example, if I retrieve information about a student in CMP322 course, the next student I would be probing is probably again from the same course, because the reason I looked for the first student was because of that course. So I would be expecting to find the next student again from the same course. So it would be a nice idea to put the students who are taking this course, or at least to put CMP students in close vicinity, so that the next information I need is probably found there. So that would be, for example, an idea in storing a database system. This would improve my performance in a database system. But if I cannot find it there, like there is a student from the math department in this course at the moment. So if I search for that student and her record is not on file, it's not in the cache, well, what will happen? It's not an error. It's just that looking at the cache was not the greatest idea. I will have to go to the full database, find that student's record, bring it here, and use it. Okay, so it would just be a degrade in performance, but it still would be working. The results would not change. That's the important thing. If the cache is smaller, then I will not be able to put too much information in the cache. But typically, if the cache is expensive, so I cannot make it too large. Also, if the cache itself gets too large as the main memory, well, then why do I have main memory? If cache could be as large as the main memory, I would just throw away the main memory and use the cache. I cannot do it because, as I said, it's too expensive compared to the main memory. And also, searching for something in a small group is faster. That was the basic idea. It's just like, assume that I have blue marbles in my hands, and it's all blue marbles, but one is red. And I ask you to find that red marble in a group of marbles in my hand. It would be an easy task. Now, consider a large classroom filled with blue marbles, and there's only one red marble in it. And I ask you to find that red marble. So, finding something in a small set is also faster. That's why we make use of cache, because if the cache is not too small, we can come up with algorithms that are feasible to find it in a very short time. Managing the cache is an important design problem. If you make it too small, it would be useless, because if it's too small, what you're searching for probably will not be in the cache because your cache is very small. If you make it too large, then it would be very expensive, and as I said, at some point it might even get slower. So finding the correct size for cache is one problem. Given some fixed size, then which of the data from the data on the main memory, in the main memory, should be brought into the cache and which should be left out? That's a major problem. So finding the size is a problem, but when the size is fixed, what should be in cache and what should not be in the cache? That's a problem. Initially, when the cache is completely empty, whatever you need, bring it to the cache. But at some point, the cache will be full. So next thing you're going to look at will not be in the cache. You'll get it from the main memory. And you would like to put it in the cache. But since the cache is full, you have to kick something out of the cache. That's what we call the replacement policy here. Something in the cache is to be replaced. Which one do I replace? If I make a good guess, great. But what if I picked the one which was the next thing to be used, but I didn't know the future? So by mistake, I thought it would not be used. So I don't use it. So I replace it. And next thing I look, I say, shoot, I wish I had not replaced that one, but it's done. Now this will again cause a degrading in performance, but still the results should not change. Now I come up with an algorithm which can guess the future better than yours, then my cache replacement algorithm is better than yours. But how you do it is really a tricky problem. We will talk about that by the end of the semester. Now, we said the device controllers hide the details of individual devices behind, like The disk controller hides the details of different types of disks, different number of platters, cylinders, whatever, all that detail from the CPU and memory. It also, remember, brought the information from the very slow disk into the local buffer in the device controller so that the CPU can read it faster from the local buffer of the controller rather than the disk itself, which was extremely slow. Sorry. However, there will be cases even reading from the device controller would be a slow process. More important, especially for the case of block devices, not character devices, which means devices that are read not byte by byte, but block by block. For example, you read 1 kilobyte or 4 kilobytes of data from the disk at once. For such devices, for such cases, the CPU cannot take 4 kilobytes into the registers. Actually, the CPU wants to put these 4 kilobytes somewhere in the memory. Now, you first bring it from the very slow disk to the local buffer, but then the CPU, byte by byte or word by word, has to copy from the local buffer of the disk controller to the main memory, which is again quite time consuming, faster than the previous one, but still slow for us. So we have another device in the system, another component, which is called DMA, which stands for Direct Memory Access, DMA. After the device controller has brought the information from the device into its local buffer, the CPU tells the DMA to read from the local buffer and to write in the memory, or vice versa. It could be the other way around. The CPU might tell the DMA to read from the main memory, to write to the local buffer so that it could be later transferred to the device, to the disk, for example. Such operations are done by the DMA rather than the CPU, so that for the CPU, it would be just a couple of messages exchanged with the DMA saying from where it should read from the local buffer, which local buffer, how much, and where to put in the memory, because it also has to tell the address in the memory. So that's all the CPU does. The rest is left to the DMA. DMA does that for the CPU, and when it is done, it will inform the CPU with an interrupt. But the CPU does not have to deal with this byte by byte or word by word transfer. So DMA is used for high-speed I/O devices able to transmit information at close to memory speeds. The device controller transfers the blocks of data from the local buffer storage directly to the main memory without the CPU intervention. The CPU intervenes only at the very beginning to talk to the DMA, saying transfer it from this buffer to this place in memory, so many bytes, and that's it. The rest is managed by the DMA, and only one is interrupted for the whole block rather than for each byte or word. If the CPU was doing this, it would be interrupted for each word. Here, for the whole block, it's only interrupted once when the operation is completed. So on a modern computer system, you will have the main memory, remember, which is volatile. In this figure, we're not showing the hard disk. That's also there, but for the moment, ignore that. This is the von Neumann architecture you're discussing, the basic von Neumann architecture you're discussing in CMPE322. In the CPU, you have your cache, which is keeping the most recently used instructions or data for faster execution. You can have one or more threads of execution, especially this will be important when we talk about threaded programming, and also when we talk about the cores. The CPU will deal with these threads. A thread is actually a sequence of instructions to be executed one after another. When those instructions require an I/O operation, the I/O request will be sent to the corresponding device. Data exchange will be done between the CPU and the device, and interrupts will also be sent. But the DMA comes into play here. Typically, the CPU will tell the DMA to do this operation, and DMA, rather than making CPU to manage all the data movement this way, instead DMA will do it directly between the device, actually between the buffer of the device controller for this device and the relative memory space here, which is to be used for the transfer. DMA will deal with this detail, and when it is done, it will just interrupt the CPU saying we're done.